you can take a whole image in the coronal green line that is showing the emission of actual iron, highly ionized atoms, iron atoms that have 26 electrons. So you know it has to be hot. And in fact, it was the identification of this line that proved that the sun is very hot. It took 70 years after the line was discovered to realize where it came from. In the interim, they had just said it came from coronium, which, as you know, is not in your periodic table. But when it was first discovered, there were a lot of gaps in the periodic table. It had nebulium and coronium, and Sun works with nebulium, and I work with coronium. And nebulium, and they both turned out to be highly ionized atoms, although the nebulae are not as ionized by 2 or 3 or so times, and mine are ionized by 13 or 15 or even 20 times because it's just so hot. Yeah. To get a Fabry-Perot, you can get a whole series of interference patterns and overlap them, and finally knock out all but some center one. And we had a resolution of 1/6 of an angstrom, which is very, very narrow, and could study the motions in the corona in that way. Now, some new techniques of adding together images and doing masking of various images to bring out details has been worked out by Miloslav Druckmuller in Slovakia. I had worked, in fact, 20 years ago in using a computer to putting together several images to bring out structure, and he has really advanced this field. So he's put together some of my images here, and you can see how far out you can see the corona into space, and you can see the structure enhanced. Here are these polar tufts I talked about before, and here are some of the coronal images we talked about before. So we actually have just submitted a joint paper to the Astrophysical Journal along with Dr. Vojto Rushin from Slovakia and a colleague of his, Dr. Metod Senega, and we can talk about these very high resolution images and what they tell us about the sun that we didn't know before. Here is a more processed image put together with the outer corona image from SOHO. And then there are models of the magnetic field of the sun based on looking at the photosphere to try to predict what the shape of the corona will be. And our images have been used to test that. And some of those predictions are improving. Druckmuller himself made some observations from Libya of a very high resolution. And here the contrast again is enhanced to show these polar tufts, for example. And then if you really do an unsharp mask and bring out the detail, you can see a number of features. There are these very narrow and curving threads. Here are some prominences. There are some dark regions that come through. Look at these curving threads here that are really unexpected. Here's some features like that. Here are the polar tufts seen in great detail. There are some more curving threads. There are some very narrow structures. You can see structures in the base of some of these streamers. Look at this non-radial structure. So we're trying to understand all these features that you can see now when you do this very highly processed imaging. And here we see a nice cavity under this helmet streamer, and we see Bailey's beads coming out, and the chromosphere at the edge of the sun as the eclipse ends. So that's a real advance in being able to see detail on the sun. I'm going to go on now, as soon as it shows here, to show you the next eclipse path, which will be on August 1st, 2008, which is only a year and a third from now. It goes over Greenland and comes down through Russia. It goes over Novosibirsk in Siberia, which is probably where we will go for that one, and then comes down and ends, doesn't reach Shanghai, and there will be certainly people observing up here in China and in Mongolia. Here is the track that starts in northern Canada, goes over Greenland, not too far from the North Pole, and comes down through Siberia here and into China. These paths are now available from Google Earth, and Xavier Jubier has put together the data from Fred Espenak and Jay Anderson, who made some of the maps I'm showing. Has provided weather and climate information weather statistics along the path. If I have now put links to all these on a website we run for the International Astronomical Union, Working Group on Eclipses. It's at www.eclipses.info. And you can get links, for example, to the programs that will give you all the details here and show you the path and show you, and you can zoom in and see the path. And here we are in southern Siberia with Novosibirsk, right over there, very near the center line, with this university to collaborate with. And I'm collaborating with Dr. Irena Kim of the Sternberg Institute, University of Moscow. And we hope to make some observations together next year on that. So here's Novosibirsk singled out. And then these are, it comes down through here, right near Xi'an, but very low in the sky, and doesn't reach Hangzhou or Nanjing or Shanghai. But the situation then, and then here are the cloud percentages here, and the tanner it is, the more desirable. So up at the edge of Mongolia, in the Gobi Desert, they don't have much cloud there, but the forecasts elsewhere in the path are in the 30 to 40% range of cloud cover. Here's some more detail. 30% or so here. The eclipse that we're all looking forward to is a longer eclipse on the 22nd of July in 2009. It will actually start in India and come across Bangladesh, and then China, passing very near Hong Kong. The peak will be out of the ocean, but right here at the edge of China, it gets up to 5 minutes and 45 seconds. And I am proceeding with my wife to Beijing on the 22nd to meet the chief Chinese solar astronomer in charge of eclipses there, Dr. Yu Yan, and he will come with us to, and also with the director of the Beijing Planetarium, to Shanghai the following few days to look for sites between Shanghai and Hangzhou from which to observe the eclipse. So here's Shanghai, here's Hangzhou, and we can probably go right over there as the leading possibility at the moment. Since it's an ellipse, the difference right in the central portion of totality is not too great. Right in the center line here is 5 minutes and 45 seconds. It's actually 5 minutes and 5 seconds in Shanghai, where for reasons of pollution you wouldn't want to be. But that's the reason. There are people talking about going out here. There's Iwo Jima and some little island near Iwo Jima. You can get access. There's some military control from Japan, and there's a lot of discussion of trying to get there. Here's the path as it crosses China over here. And some people go to Wuhan, where it's 5 minutes and 15 seconds of totality. We're going to try to go over there. The cloudiness varies a bit, but is average amount of cloud close to 50%, 50 to 55% along this whole region over there. You don't want to be India, Mumbai, 75% chance of failure. This is as good as it's going to get without eclipse. The statistics are now available. And then as far as the track here, you see it's a little better for this whole region. Well, then here are these few difficult to reach Japanese islands and Iwo Jima out here where it's a little lower. You can go in and Google Earth and see Shanghai and see Hangzhou, and there's a little port city over here where we're going to look certainly next week, and I just don't know where else around here you might be able to get. There are various tourist groups. Most people go for a day and can really just drive out from Shanghai or Hangzhou. With our scientific equipment, we have to be on site for a week or 10 days, so we need facilities, we need security, electricity, place to live, etc. for a team of, well, in Greece it reached 42 people, and so we're working on those logistics. We do a year in advance, and here again is where we might be able to get. As I said, we have a website at www.eclipses.info that I run for the International Astronomical Union. We have a program group on public education on the occasions of solar eclipses, that parts of the Commission on Education and Development, and the working group on solar eclipses. Since I'm head of both groups, there's kind of an overlap there, but we're very interested in the educational aspects, getting the attention of tens of millions of people who will be in the zone of totality in Hangzhou and Shanghai and Wuhan, not to mention hundreds of millions of people who will see a deep partial eclipse, who can use some education, and we will certainly get their attention when the sun is taken away in the middle of the day, and you can use that for all kinds of teaching. You can teach some science, you can teach some astronomy in particular. You can also just teach the general idea that we understand the world well enough to make predictions like this, and that if you go to school and you study, you too can understand the universe, and you can have a big effect on students if you take this occasion to educate them on what's happening. On this website, we have some links to this Google Earth and Google Maps sites, and some other people are also making maps, and the Anderson maps, of which I've just shown you a few, are linked there. So just remember eclipses.info. Let me take a few minutes then to mention this elaboration of the eclipse work, in which while I was looking at the sun, I had the techniques of using the TRACE spacecraft and observing the sun to take advantage of transits of Mercury and Venus. This matter first came to my attention when I went to a meeting of the American Astronomical Society and heard a historical paper about transits of Venus, in which the speaker, Brad Schaefer, said that he looked at a number of published articles and books about transits of Venus, and more than half of them had an incorrect explanation of what is known as the black drop effect at the edge of Venus when it goes inside the sun, claiming mistakenly that the black drop effect shows the atmosphere of Venus. I realized that with my solar work, I had the ability to use the TRACE archive to look at that time at existing data from transits of Mercury. Now, transits of Venus are very rare, and nobody on Earth had seen a transit of Venus since the previous one had been in 1882. The transits of Mercury are somewhat more common, in that there are about a dozen per century, and there had been one in 1999, and those data were available in the TRACE archive, and I brought in Glenn Schneider from the University of Arizona, and we could see that there was a little black drop effect at the edge of the image of Mercury, at the edge of the sun, for a couple of minutes in this grazing transit of Mercury.